Here are solutions to homework set number 5 for ECE 341 random processes. This homework looks at geometric and Pascal distributions. Now, a geometric distribution is when you flip a coin until you get a success. A Pascal is you flip a coin until you get R successes. So starting out, problem 1. Going to roll a 10-sided die until I get a 1. That's a geometric distribution. Problem 1 is find the PDF using z-transforms, and from the z-transforms, or from that solution, find the probability A is 10, and the probability A is at least 10. Well, from the lecture notes, the z-transform, also known as the moment-generating function for a geometric distribution, is p over z minus q. So that'll be 1/10 over z minus 9/10. Basically, I flip a coin, or roll a die, 90% chance I don't get a 1. Keep on doing that until I get a 1. The last time I do it will be the 1/10. So to find A of k, I need to take the inverse z-transform. This isn't in the form, this is in my tables. So one trick is to multiply both sides by z. Now this is in my table. The inverse z-transform is 0.1 times 0.9 to the k u of k. To get rid of the z, divide by z, which is delay by 1. So k's go to k minus 1. And there is your PDF for A of k. From that, I can plug in A equals 10 and get 3.8%. For k greater than 10, kind of two approaches. I could find the CDF, but that'll be work. Or use MATLAB. Just let k go out to 1,000. Should go infinity, but as at 1,000. Here's A of k, and then sum up all the terms between 10 and infinity, and you get 38%. So that's problem number 1. I'll kind of mention the CDF. What the CDF would do would be integrate this. Integration is z over z minus 1. So if we take A, z minus 9/10, that's the PDF. Integrate, which is times z over z minus 1. That's the CDF, cumulative density function. That's the probability that k is less than or equal to 10. So if I do this, I'll add all these up. That'll give me the converse of this. What's that? 62%. Area of the tail then is 1 minus that. But anyway, that's problem 1. Problem 2. Repeat problem 1 using Monte Carlo. So with Monte Carlo, I am going to start with one die roll, keep on flipping until I get a number less than 1/10. The number of flips is n. So I'll do that and keep track of how many times I have n die rolls until I get 1 on a 10-sided die. If I do that 100,000 times, then 3845, or divide by 100,000, 3.8% of the time I got the number 10. 38% of the time I got number at least 10. So comparing them, calculated matches Monte Carlo. If I run Monte Carlo a second time, I'll get a different answer. It's random, but it's close, so it's right around 3.8% or 38%. Problem 3. Problem 3 is a Pascal distribution. I'm going to toss 2 dice. 1, I'm going to roll until I get a 1. That's A. Let B, I'll then roll until I get a 1 or a 2. X is the sum of A and B. Find, using z-transforms, the PDF of x and the probability x is 20, x is at least 20. So to do that, I would take, here's the z-transform for A, z-transform for B. For x, you multiply the z-transforms. So this is where the z-transforms really shine. This is a whole lot easier to do than convolution. To find x of k, find the inverse z-transform. So again, multiply by z to get a z in the numerator. Pull the z outside, do partial fraction expansion, multiply through by z, take the inverse z-transform. To get rid of the z, divide by z, so everyone shifts by 1. So that's the PDF for x. And with that, I can find out what's the probability. It's going to take 20 die rolls, 2.4%. probability it takes at least 20 die rolls, 25%. And as a check, if I add up all the x's, all probabilities add to 1. 1,000 is kind of a number pulled out of the air. This should go out to infinity. I stopped at 1,000, just figuring that's good enough. And the area being 1 says I did lose a little bit of area, but at least I can't see it to 4 decimal places. Kind of sidelight where I picked the number 1,000 is the mean of this is 10. So I picked it to be 100 times as long, which usually 10 times further is good enough. I used 100 just to make doubly sure. Problem 4. Repeat problem 3 using convolution. So here I took it out to 200. That's 20 times the mean. Here's the PDF of A, PDF of B. Convolve the two. Checking to see that I took it out far enough. The area is 1, so it's probably about right. To find out the PDF of x of 20, I take x of 21. Again, the reason for 21 is MATLAB doesn't like the index 0. X of 0, MATLAB hates. X of 1 means k equals 0. X of 2 means k equals 1. So 21 means 20. And then summing 21 out to infinity, I get 25%. Same answer. Third way to solve, Monte Carlo. I'm going to toss a die until I get a 1, toss a second die until I get a 1 or 2, add the two together, and keep track. How many times did it take 1 roll, 2 rolls, 3 rolls, 4 rolls, and so on. Repeat 100,000 times, and here's what I get. Probability that x is 20 is 2.4%, or 2413 in 100,000 rolls. First Monte Carlo, second Monte Carlo, it's about the same ballpark. Number times x was at least 20, it's about 25%. So again, looks like we did it right. Last 3 problems are repeat, but with 3 die rolls. So roll until I get a 1 on a 10-sided die, 8-sided die, 6-sided die. Y is the sum of the die rolls. First, find y using z transforms. So here's the PDF of A, B, and C. Multiply them all together. That's the z transform of y. To find y of k, take the inverse z transform, can multiply by z, do partial fraction expansion, multiply through by z, take the inverse z transform, delay by 1. Okay. All said and done, there is y of k. And there's a couple other ways of doing it. Should all be equivalent. To find the probability that y is 20, I plug in this for k. At 20, 3.4%. At least 20, 56%. Checking. If I use convolution to find A, B, and C, I get 3.4% for 20, which actually 21, index 21 means 20. 56% for 20 on up. That matches up. Third approach, using Monte Carlo. Roll a 10-sided die until I get a 1, 8-sided die until I get a 1, 6-sided die until I get a 1, add them all up. Keep track of how many times it took 1 roll, 2 rolls, 3 rolls. In 100,000 rolls, it was 3.3% on Monte Carlo. Pretty much matches calculations. 56% for at least 20. Matches calculations. So it looks like we did it right. So that was homework set number 5. And we've got a couple different tools. We can use the moment generating function, or z transforms. I can use convolution with MATLAB. I can use Monte Carlo with MATLAB. All 3 approaches should give you about the same answers. Monte Carlo is easier, but the first 2 are actually more accurate. Homework set number 5 for 341.